Okay, so we are going to start with the V-stock and spin models.
Okay. Hello, everybody. My name is David Zarate-Herrada. I'm from Benemérita Universidad Autónoma de Puebla, in Puebla, Mexico, and I am doing a brief internship at UConn. The name of my talk is Disorder Spin Models. When I prepare this talk with basic concepts to understand how we can study these models. These models. Okay. Well, I'm going to start explaining you about of the two-level system. For example, is if we have an electron, and if we apply a magnetic field, we can get two possible states. One state with lowest energy, in this case equal to minus epsilon over 2, and another state with highest energy equal to plus epsilon over 2. The both states can be right like this, get down and get up, and we refer to get up like an excitation. Okay. Well, the Hamiltonian for this two-level system can be right like this, epsilon over 2 by sigma zeta, where sigma zeta is sigma zeta, sorry, where sigma zeta is the Pauli's matrix in zeta direction, and this Hamiltonian acts over on these states like this, and
Like this, you can point.
uh,
Mm.
like this, and we can note that uh, the we can note that these states are eigenbases for this Hamiltonian, okay, where its respective uh, eigenenergies are epsilon over 2 and minus epsilon over 2.
Mm.
Okay, now uh, we are going to consider a system with two coupling spin-1/2 particles, where all possible states for this system uh, are this. Now we are going to study an Ising type interaction term, and this term looks like here, this. And this term interaction acts on these in these elements like this. Um, the elements of this basis I have labeled with two different labels. The first label one correspond to the first particle, and the second level two correspond to the second particle. This term, in this term, we can see that we have the Pauli's matrices uh, that acts only the state on the first particle, and another um, Pauli matrices in zeta direction that only acts over the second, the state of the second particle. Yes, we can see that we get the lowest energy when we have an anti-parallel spins for this system.
When J is positive.
Yes, when J is positive, in principle. Okay, we can move on excitation using the next term. This term here is named the flip-flop term, and this term has the next operators, sigma x and sigma y, where sigma x and y are the Pauli's matrices in the x and y directions, and these operators acts on these states like this. And if we ap apply this operator on the on these states, we can see that the excitation moves to the next position. Okay, you can see this. Any question about this?
No, this was good.
Okay. Now, if we consider a system with L spin-1/2 particles, like a chain, the Hamilton for this system is named the Heisenberg model. This looks like this, where this Hamilton is integral. This in the sense that we can get all possible eigenstates and all possible eigenenergies by analytical methods. Now, if we apply a random magnetic field, H sub I, where H sub I are random numbers from a flat distribution, then the model becomes a non-integrable model. This term of here applies a random magnetic field where generates random Zeeman splitting in the energy of H spin-1/2 particle in the chain, such that the probability that excitations move to the next position is random. Okay, now if we consider a chain of L spin-1/2 particles with magnetic field in the zeta direction for each position, we have the Heisenberg model with disorder. Here we have fixed J equal to 1, where J is coupling constant. We have the Heisenberg model with disorder. This model conserves the total spin in the zeta direction. We can study this model by its energy spectrum and its components of its eigenstates. For example, using the exact diagonalization. Okay. We can study its spectrum using the level spacing distribution. If we calculate this spacing, where the spacing are the difference between consecutive eigenvalues, and if we calculate the distribution of this spacing, we can get the level spacing distribution. If this distribution match with this Poisson distribution, that's mean that the spectrum doesn't have repulsion between the levels, and this means that its eigenvalues are uncorrelated. But if the level spacing matches with the big generalized distribution, that means that we have repulsion between levels, and that means that the system has eigenvalues correlate. Okay. This model with disorder has the next behavior. For example, if we calculated the level spatial distribution for values of H less than 1, we can see that the level spacing distribution match with the Wigner-Dyson distribution. And this behavior is typical for random matrices. And if we calculate the level space distribution for some value of h after um, larger than critical point, we can see that its level spatial distribution matches with the Poisson distribution. If the system present this behavior, we can say that the system has many body localization. Yes.
So what you're saying is that Wigner Dyson is associated with a delocalized phase, and Poisson is associated with a localized phase. We don't know yet why. You're going to explain to us, right? And in between here, as you increase in the value of this disorder, you don't have either Wigner Dyson or Poisson. You have something in between, right?
Yes,
Okay,
we have a mixed distribution.
Okay, so now you're going to explain to us why you're telling us that Wigner Dyson means delocalized and the Poisson means localized. Okay, let's see.
Okay. Now, we can study now also we can study the information by the its eigenstates by some quantity, namely the inverse participation ratio, where given an initial state when it can be this. The IPR for our initial states looks like here. With these components, C sub alpha are the projection between our initial state with the eigenstate of the system. One feature of this quantity is that the IPR scales with the system size like this. The value of this exponent tell us the information about of the type of the type of the type of this eigenstates. Okay, if we have the gamma is very close to zero, see, yes. If we have gamma is very close to zero, we have the localized states. And if gamma is very close to one, that's mean that we have extended states.
Why?
Because the IPR measures the level of localization of the eigenstates on certain basis. If the IPR is equal to or is very similar to n up to -1, that's mean that all eigenstates contribute in the construction of our initial state.
Very good. And which case do we have according to the level statistics?
Yes, because I don't remember this part.
But the level statistics, the Poisson is for which case? This one, or this one?
Yeah, yes.
Where do we
Yes,
get Poisson?
okay. If gamma is close to zero, we have that the system shows a level statistical of type Poisson. And if we have gamma is equal to 1, we have the system shows Wigner-Dyson level.
Okay. So now we understand. Okay.
Leveling statistics. And if we have that gamma is between 0 and 1, we have states neither localized nor extended. Okay. For example, here, this is a scaling analysis of the IPR for the XX, well, for the Heisenberg model with disorder for different values of H. Um, you can see that um, you can see that when H is equal to 1, the value of the exponent gamma is very close to 1. That's mean that we have a spectrum. No, that's mean that the system shows a level spacing distribution very like a Wigner-Dyson distribution. Also, that's mean that we have extended states, and when we increase the value of H, we can see that the value of this exponent gamma decreases, and that's mean that we have states neither localized nor extended. Yes, this scaling analysis was did
Done.
was done was done for system size. Um, we put an initial state with the energy very close to 0.
So the initial states he picks spin configuration. So some spins are pointing up and some are pointing down. He looks at the half of them are up and half of them are down because that's the largest subspace that you have. Okay, and then you have all possibilities. No, but from all of these many possibilities, he's going to look at the one that has energy closer to the middle of the spectrum. The density of state is Gaussian, so he's going to go in the middle where there are many states.
Okay. Well, the next part. I'm going to explain you a way to get the Heisenberg model by analytical approach. Now we know that if we have a quantum system, we can solve the Schrödinger equation to get all eigenfunctions and the eigenenergies for a particular quantum system. We know that. Okay. The first approach for to solve this system with the spin information is relevant. We know that the wave function of this system can be writing like a product of the two functions. The first function has all the relevant information about the spin, yes, and the other function has the information of the spatial coordinates in in, in the space. And for example, for this example, we are going to work with a two level system of two coupling particles. Again, the operators that describe this this kind of system is the spin operators, when you can know that we are using the this we are using units of h bar, and if you remember that the square of these operators are equal to the identity matrix over 4 by 1 over 4. Also, we know that the spin operator in theta direction is diagonal, and its eigenstates are yes, eigenstates are get up and get down. Okay. Also, have I have wrote the eigenstates for the the spin operators in x direction and y direction, and we define the complete spin operator in the three directions, in three Euclidean directions, like this, where we know that the square of this operator looks like this, and its eigenvalue is 3 over 4, when P is an eigenstate of this operator. Okay. For a system with two coupling spin 1/2 particles, we know that we need to apply the Pauli's principle. That's mean that we need to put some conditions about of the antisymmetry of our wave function. In this case, we know that if es que no veo acá. Aquí veo. We know that if our uh, spatial wave function is symmetric, the function that has all the information about the spin must be antisymmetric, and vice versa. How do you say
Vice versa.
Vice versa, right? Vice versa. If our wave function is antisymmetric, the function with this information of the spins must be symmetric. Okay. We know that when we solve the Schrodinger equation, the energy only depends of of the the wave function that has the information about of the coordinates. And if we don't consider interaction with the particles, we can we can split, yes, our wave function for these two particles in the product between these two new wave function, and we can we can put the wave function, the symmetric wave function like this, and the asymmetric wave function like this, where this symmetric wave function correspond to the spin quantum numbers when S is equal to 0 and ms is equal to 0 also, and the wave function in the when the wave function is antisymmetric, we set the spin quantum numbers equal to S equal to 1 and ms equal to -1, 0, and 1. Okay, we can get the energy for the symmetric case and the energy for the antisymmetric no case. Well, the symmetric case, where um where this condition is true. Okay, the energy for the symmetric case looks like this. And the energy for the antisymmetric case looks like this. Well, where the difference between both energies looks like this. Now, the Hamiltonian that describe this system looks like this, where we have this spin operator that only acts over on the first particle, and this only acts on the second particle, where the operator, the spin operator, total spin operator for this system looks like this, and the square of this looks like this. Okay, so the eigen, we know that the eigen energy for this operator is S by S plus 1, when S, when we have two eigenvalues equal to 2 if S is equal to 1, and 0 if S is equal to 0. And the eigen energy for this operator is this, and this for this Hamiltonian. Okay. Now, using the real basis that I said previously, we can we can put we can get the correspond eigenstates and eigenenergies for the triplet for these quantum numbers. And we can know that these three eigenstates are symmetric, and this eigenstate is antisymmetric. This is the triplet, and this is the singlet states. So with this information of here, we can write an effective Hamiltonian. This Hamiltonian, you can check this. It give us the value of the energy when we apply the triplet and singlet, and we can cannot we have this constant term of energy, and it can be absorbed in another terms of the energy, and we have this term that we have calculated previously. So if we substitute this term of here with this integral, we can rename this integral with J. With J is the exchange constant. Okay. And the Hamiltonian can be written like this. Okay, so J is this integral in the space. Okay. That's mean that if now we consider a system with many spin-1/2 particles, the Hamiltonian for this system is the Heisenberg model, and this looks like this. When if we only considering um, uh, interactions between peers neighbors, we can reduce or simplify this exchange constant, like only It's like a constant. And if J is positive, that's mean the interaction of these two spins favors the favors to them to be parallel. And this corresponds to the ferromagnetic case. And if J is negative, the antiparallel orientation is power. That is the antiferromagnetic case. This is all.
Okay, thank you, David. I don't know if people have questions. I have many questions,
Okay.
but I'm going to